The title of section 3.4 is Additional Topics in Probability and Counting. And basically, what we're going to be doing in this section is talking about permutations and combinations. And we do have some kind of tricky applications to do towards the end. So let's get started. A permutation. A permutation is an ordered arrangement of objects. So when we're dealing with permutations versus combinations, in a permutation, order is important. In a combination, it's not going to be important, and we'll get to that later. To find the value for a permutation is if you have n distinct objects, then there are n factorial ways to arrange all of them. So when we're working with, I said that's name is n factorial, but I'm going to write down that the way we pronounce that is n factorial. That exclamation point means factorial. And what that means is that we're going to take n times n minus 1 times n minus 2 times n minus 3 all the way until we get to 4 times 3 times 2 times 1. That's how we do n factorial. By definition, 0 factorial is equal to 1. I know that doesn't make sense, but it is what it is. So in your calculator, you can find that factorial button in the math menu, arrow over to probability, and then choose number 4, which is the factorial button. So let's practice that a little bit. So 5 factorial. If you go in your calculator, you need to put the 5 in there, and then the math menu also right there, and then go over to probability, and then choice number 4 is that exclamation point, and that value is going to be 120. The way that it's calculated is by doing 5 times 4 times 3 times 2 times 1. You do that in your calculator, you also get 120. So when we're using just n factorial to arrange objects in order, what's important is that we are using all of the objects. So here I would be arranging, 5 different colored markers in some kind of order. There would be 5 different ways for me to arrange those. So orange being first, and then orange being second, third, fourth, fifth, and then I can move all of these around. There would actually be 120 different ways for me to arrange those markers. And you'd be able to tell them apart from each other. So let's use this idea of factorial. The objective of a Sudoku puzzle is to fill the grid so that each row, column, and 3x3 grid contain the digits 1 to 9. They want to know how many different ways can the first row of a blank 9x9 Sudoku grid be filled. So we're working with filling in this grid with those numbers 1 through 9. So what we want to do is arrange 9 distinct objects because it's the numbers 1 through 9. And we are using all 9. And order matters. I'll be able to tell if it goes 1, 2 versus going 2, 1. So when all of those conditions are met, we're arranging 9 distinct objects using all 9 and order matters, then the number of ways to do that is found by doing 9 factorial, which is 9 times 8 times 7, 6, 5, 4, 3, 2, 1. And you can multiply that out by hand on your calculator, or you can use that factorial button. 9 math over to probability, number 4, to get the answer of 362,880. So there are 362,880 ways to fill in an empty row on a Sudoku puzzle. The women's hockey team that qualified for the 2014 Olympics are Canada, Finland, Germany, Russia, Japan, Sweden, Switzerland, and the United States. How many different final standings are possible? So again, we have 8 distinct objects. We are arranging all 8, and order matters. So the solution to that would be 8 factorial, which if I do that in my calculator is 40,320. So there would be, if we just used different arrangements, there would be 40,320 different ways for those 8 teams to end up at the end of the Olympics. Now, we may not always want to arrange all 8 of our objects or all 9 of our objects. So when we do that, it's called a permutation of n objects taken r at a time. So let's write some stuff down. You may only want to choose some of the objects to arrange in order. So, for example, I may ask the question, how many ways would there be to win gold and silver? So now I don't want to arrange all 8 of my objects. I'm just going to have 8 objects, but I'm going to choose 2 at a time because I only have 2 places for gold and silver. So there's a formula for that, and there's a notation. So the N and the R are what we call subscript. And the formula is that we will do n factorial divided by n minus r factorial. So this is actually a permutation. Permutation is arranging things when order is important. So it's a permutation of n objects taken r at a time. So this is the formula that we'll use when we have a certain number of objects that we're arranging in order, when order matters, but we're not going to arrange all of them. We're only going to arrange some of them. So the notation I would use here would be I'm doing a permutation of 8 objects taken 2 at a time. So that's going to be 8 factorial divided by 8 minus 6 factorial. 8 minus 2 factorial. Sorry about that, which is 8 factorial over 6 factorial. So one of the nice things about this kind of this formula is that I don't have to calculate 8 factorial all the way down, because what's going to happen when I do 8 times 7, 6, 5, 4, 3, 2, 1 is when I have 6 factorial, a good portion of that numerator is going to cancel off. So all of the 6, 5, 4, 3, 2, 1 is going to cancel with the 6, 5, 4, 3, 2, 1 in the denominator. So all I really have to do is 8 times 7. So there would be 56 different ways for those 8 teams to finish gold and silver. One thing that's important to remember is that the first number here will always be larger than the second number because we're taking out of a pool of 8, we're choosing 2 out of it. Now there is a place in your calculator to do this. It is also in the math menu. You arrow over to probability, and it's going to be choice number 2, which is NPR. I'll show you that. So if you go to the math menu, arrow over to probability, choose number 2, NPR. My calculator gives me spaces to put those numbers in, so I'll put an 8 here and a 2 here, and then enter, and that gives me my answer of 56. Now, please be aware, as I'm sure that you are, that on your test, I will ask you to calculate this by hand. So I am going to want to see that you know how to apply this formula, n factorial over n minus r factorial, and work out the answer. Yes, using a calculator, but not using that feature of the calculator. Okay, so let's do a few more of these. If I am going to arrange 10, let's see, find the number of ways of forming 4-digit codes in which no digit is repeated. So I have 10 objects that I'm arranging. They are 10 distinct objects. They are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I'm choosing 4 of them at a time. So I'm going to arrange 4. Order matters because I will be able to tell the difference between 1, 2, 3, 4 and 4, 2, 3, 1 when I have my code. So the way that I'm going to do that is I will have a permutation because order matters, 10 objects, and I'm choosing 4 of them. So in my formula, I'll have n factorial, so 10 factorial, divided by 10 minus 4 factorial. So 10 factorial over 6 factorial, which works out to be 10 times 9 times 8 times 7, because then the 6, 5, 4, 3, 2, 1 cancel off. Which is 5,040. A psychologist shows a list of 8 activities to a subject in an experiment. How many ways can the subject pick a first, second, and third activity? So we have 8 distinct objects. Order matters because we're going to pick a first, second, and third activity. So if I do a puzzle and then a drawing and then listen to music, that's different than listening to music and then doing a puzzle and then drawing. So order matters. And we're going to pick 3 to arrange. So that's going to be a permutation because order matters. I have 8 objects and I am picking 3. So that's going to be 8 factorial divided by 8 minus 3 factorial, or 8 factorial over 5 factorial, which would be 8 times 7 times 6. So 336 different ways to choose those 3 activities. I do want to go back up to this formula here, and I want you to notice something. What I want you to notice is that with this formula, NPR, if I arrange all of the items, all of the objects, then my NPR becomes NPN. And then in my formula, I'll have n factorial divided by n minus n factorial, which is n factorial over 0 factorial. And up at the top of the page, I told you by definition, 0 factorial is 1. So this is n factorial divided by 1, which just becomes n factorial, which is how we started at the beginning, which is if you have n distinct objects and you're arranging all of them, there are n factorial ways to do that. So instead of remembering two different rules, you can always just use this rule and it will still come out the same way. Let's do some more problems. 43 race cars started the 2013 Daytona 500. How many ways can the cars finish first, second, and third? Well, let's ask ourselves those questions. Does order matter? In other words, will I be able to tell the difference between, Bob, Joe, and Bill winning first, second, and third versus Bill, Joe, and Bob? Well, I'm pretty sure they will know the difference of who won first, second, and third. So order matters, which means it's a permutation. I have 43 different race cars, and I am choosing them 3 different slots. So I will have 43 factorial divided by 43 minus 3 factorial, or 43 factorial over 40 factorial, which will be 43 times 42 times 41, which if I put that in my calculator gives me 74,046 different ways for that Daytona 500 to end up. The board of directors of a company has 12 members. One member is president, another is vice president, another is secretary, and another is treasurer. How many ways can the positions be assigned? So order is important here because it's different if I'm the president versus being the treasurer. So order is important, which makes it a permutation. I have 12 members, and I am choosing them for 4 different positions. So it would be a permutation of 12 objects taken 4 at a time. So 12 factorial divided by 12 minus 4 factorial, or 12 factorial over 8 factorial. So basically 12 times 11 times 10 times 9, which comes out to 11,880. Now there's going to be times that we want to put a group of n objects in order when some of the objects are indistinguishable. So let me get you an example of that real quick. So, for example, if I have 4 strawberry and 3 root beer barrels, 5 butterscotch, and 1 spearmint candy, how many distinguishable arrangements? So when you think about that, I have 9, 10, 11, 12, 13 objects, and I'm going to put them in some kind of order. So I'm going to put all of them in a row of some sort. And I want to know how many different ways are there to figure out distinguishable arrangements. Well, I don't know about you, but if I have these in order this way, I could definitely tell the difference between this order and this order where I've switched out the type of candy. But I could not tell the difference between having this order and having this order where I've only switched the strawberry candies positions. So we need a formula for that. The formula for the number of distinguishable permutations, that means order arrangements you can tell apart, of n objects when there are groups of different types. So like 4 strawberry, 3 root beer, 5 butterscotch. So there's going to be a formula for that. The number of distinguishable permutations. Distinguishable permutations means arrangements that you can tell apart. Of n objects where there are n sub 1 of one type, n sub 2 of another type, n sub 3 of another, etc., etc. So the number of those permutations is going to be equal to n factorial, which is our total number of objects, divided by n sub 1 factorial times n sub 2 factorial times n sub 3 factorial, however many subgroups we have. So in the example of our candies, how many distinguishable arrangements would there be? Well, we have 13 candies, so that's going to be our n. So 13 factorial divided by, we have 4 of type 1, so 4 factorial times 3 of another group, 3 factorial, times 5 factorial, times 1 factorial. So we will want to do that in our calculator. Okay. 13 factorial is 6227020. And then 4 factorial is 24, 3 factorial is 6, 5 factorial is 120, and 1 factorial is 1. So we have that number divided by 24 times 6 times 120 gives us 360,360 distinguishable arrangements. Now, how many total arrangements? There would be this numerator up here, that 13 factorial. That's a big number. But we couldn't tell them apart because, like, if 2 strawberries swap spots, you wouldn't be able to tell them apart. Okay, so let's look at a couple of examples using that concept. A building contractor is planning to develop a subdivision. The subdivision is to consist of 6 one-story houses, 4 two-story houses, and 2 split-level houses. In how many distinguishable ways can the houses be arranged? So we have 12 total houses. So we're going to do 12 factorial. And then within those 12, we have a group of 6 that are the same. We have a group of 4 that are the same. And we have a group of 2 that are the same. So 12 factorial divided by 6 factorial times 4 factorial times 2 factorial. And that's going to tell us the number of distinguishable ways of putting those houses in. So let's see if we can actually do that whole thing in our calculator in one step. I'm not sure about this. So we're going to do 12 factorial divided by 6. Push the wrong button. Let's see. Is there another way to get that factorial button? Gosh, I wish there was another shortcut. So factorial times 4 factorial times 2 factorial is just 2. So I'll just type that in there. That is 13,860 distinguishable ways. Now the contractor wants to plant 6 oak trees, 9 maple trees, and 5 poplar trees along the subdivision street. The trees are to be spaced evenly. In how many distinguishable ways can they be planted? So what I want you to do is try that problem. And I'll put something in front of the camera so you can't see what I'm writing, and then we'll compare our work. So we have our contractor that wants to plant 6 oak trees, 9 maple trees, and 5 poplar trees. So that is going to be a total of 20 trees. We won't be able to tell the 6 oak trees apart from each other, the 9 maple trees apart from each other, and the 5 poplar trees apart from each other. So I have 20 factorial divided by 6 factorial times 9 factorial times 5 factorial. And then I will do that in my calculator. So I've got 20 factorial divided by 6 factorial times 9 factorial times 5 factorial. Yikers. That's a lot of ways. That is a lot of ways. 77,597,520 distinguishable ways to plant those trees. When order does not matter. So, think of it like if you are entering a contest and the top 3 winners each get $1,000. Well, you don't really care if you're the first winner or the third winner because everyone's getting $1,000. So that would be when order does not matter. So when order does not matter, then that would mean that ABC and ACB and BAC and CAB and BCA and CBA are all the same. So what happens then is that choosing these 3 people, or like the top 3 winners of the $1,000, doesn't matter what order they're chosen in. So since all of these are the same result, then there actually ends up being fewer ways to make those selections. So when that happens, we use something called combinations instead of permutations. So if order is important, we need to use the permutations formula, which is the P. And when order does not matter, we're going to use combinations, which is the C. So we use combinations of n objects taken R at a time. So that is a combination of n objects taken R at a time. It looks really similar to permutations. And actually what it is the permutation formula then divided again by R factorial. So it is n factorial divided by n minus R factorial times R factorial, because I have to divide by these combinations here. So for example, if I have 10 objects that I want to arrange 4 at a time and order doesn't matter, then I will have 10 factorial divided by 10 minus 4 factorial times 4 factorial. So that's going to be 10 factorial over 6 factorial times 4 factorial, which ends up being 10 times 9 times 8 times 7, because the 6, 5, 4, 3, 2, 1 canceled off, times 4 times 3 times 2 times 1. That ends up giving us 210. Now there is, of course, a place in your calculator to calculate that. It is in the math menu, arrow over to probability, and you might remember seeing choice 3 that said NCR. So I can do that in my calculator as well. Math, probability, NCR. take 10 objects, arrange them 4 at a time, gives me 210. Again, please make sure that you know how to use this formula and show your work by hand, because I will be asking you to do that on tests. Finding the number of combinations. So, a state's Department of Transportation plans to develop a new section of interstate highway and receives 16 bids for the project. The state plans to hire 4 of the bidding companies. How many different combinations of 4 companies can be selected from the 16 bidding companies? So we have 16 objects, which are the companies. We're going to choose 4 of them. And in this case, we need to know, does order matter? Well, they're hiring 4 of them, and it doesn't say any one of them is going to get anything better than anyone else. So we would say order does not matter, which means we're using a combination. So we're going to have a combination. We have 16 objects. We're going to choose 4 of them. So by our formula, we'll take n factorial, so 16 factorial, divided by n minus r, so 16 minus 4, which is 12 factorial, times r factorial, which is 4 factorial. So 16 factorial divided by 12 factorial times 4 factorial. (16 factorial divided by 4 factorial) and divide also by 12 factorial gives us 1,820 different combinations of contractors. The manager of an accounting department wants to form a 3-person advisory committee from the 20 employees in the department. How many ways can the manager choose that committee? So we're going to have 20 objects. In this case, they are employees. We're going to choose how many of them? 3 to make this committee. And it doesn't matter what order I choose them in. So order doesn't matter, or order is not important, which means we're using a combination. So we have a combination of 20 objects taken 3 at a time. So that's going to be 20 factorial divided by 20 minus 3, 17 factorial, times 3 factorial. So let's see if we can do that all in one step. 20 factorial divided by 17 factorial times 3 factorial is just 3 times 2. So that would be 1,140. And that would be the different committees that could be formed, because you could have Bill, Sue, and John, or you could have Bill, Sue, and Steve, or Bill, Sue, and Jennifer. Those would all be different committees. But having Bill, Sue, and Jennifer would be the same as having Jennifer, Bill, and Sue. So that's why it's a combination. Here's a nice summary and some tips on how to know which of the counting principles to use. So here they're saying to solve a problem using a counting principle, make sure you choose the appropriate principle. So to help you do this, consider these 3 questions. Are there 2 or more separate events? If so, you could use the fundamental counting principle, which tells you to multiply the number of ways for one event times the number of ways for the second event. If the order of objects is important, you'll be using a permutation. If the order is not important, you'll be using a combination. So a lot of these problems, though, are going to require you to use more than one of these counting principles. And we're going to see that in example 8 when we get to it. For now, we're going to start with example 6. A student advisory board consists of 17 members. 3 members serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve in any of the positions. What is the probability of selecting at random the 3 members who currently hold the 3 positions. So now we're not just looking at how many ways are there to make this committee. We want to extend this into finding probabilities. So we want the probability that we actually choose the current board members correctly. So in that probability, that is going to be the correct arrangement, the number of ways to get the correct arrangement divided by the total number of ways to choose 3 people. So the number of correct arrangements is actually just going to be 1 because there's 1 current board. The number of ways to choose the 3 people, we need to decide if order matters. So we are going to be using 17 objects. We are going to choose 3 of them, and we need to know if order is important. Well, it says the 3 members serve as the chair, secretary, and webmaster. So since they're serving in different capacities, we are going to say that order matters. So when order matters, we use a permutation. So we'll be taking 17 objects and choosing 3 of them. In a permutation, the formula for that is n factorial, so 17 factorial, divided by 17 minus 3 factorial, so over 14 factorial. So basically 17 times 16 times 15. So that would be 4,080. So there's 4,080 different ways to choose those 3 people. So the probability that we would choose the correct current board members would be 1 out of 4,080. Let's see what that is. 1 divided by 4,080. That's a small number. Approximately 0.000245. That's a really low chance of that happening. A student advisory board consists of 20 members. 2 members serve as the board's chair and secretary. Each member is equally likely to serve. What's the probability of selecting at random the 2 members who currently hold the 2 positions? So this is basically going to be the same as the problem we just did. So the probability that we choose the correct board, I'm just going to shorten this process a bit, would be the number of correct arrangements, which is 1, divided by the number of ways to choose 2 members out of 20 when order doesn't matter. Oh, order does matter. Order matters because I'm choosing a chair and a secretary. So that's going to be 1 divided by, since order matters, it's a permutation. We have 20 members that we're choosing 2 of. So I'm going to this time use my calculator to do the permutation of 20 objects taken 2 at a time, which is 380, which gives me a probability of about 0.00263. That brings us to the last page of examples for 3.4 is what we're on. But this page is kind of a doozy. So we're going to have to kind of concentrate our efforts. The first example, we're going to find the probability of being dealt 5 diamonds from a standard deck of 52 playing cards. So probability that we are dealt 5 diamonds out of 52 cards. So that is going to be a probability, so it's going to have a numerator and a denominator. The numerator is going to be the number of ways that we can get 5 diamonds out of the 13 diamonds that are in the deck. And then the denominator is going to be the number of ways to choose 5 cards out of the 52. So the probability that we are dealt 5 diamonds out of 52 cards. Does order matter in this problem? It just says 5 diamonds. It doesn't say like 4, 5, 6, and 7 or anything like that. So order is not important. When order is not important, remember that means we're using combinations. So the number of ways for me to choose 5 diamonds out of 13 is going to be a combination. I have 13 objects and I'm choosing 5. And the number of ways for me to get 5 cards total out of 52 will be a combination. I have 52 objects and I'm choosing 5 of those. I'm not writing this one out. This is one I'm going to just go ahead and get in my calculator. So I'm going to do the combination, 13 objects, choosing 5 of them. There would be 1,287 ways for me to choose 5 different diamonds when I have 13 diamonds to choose from. And then I'm going to take my 52 cards and I'm going to choose 5 of them. And there are a lot of ways for that to happen. So the probability that I would get 12 diamonds dealt to me out of 52 when I'm randomly handing out cards would be 1,287 divided by 2,598,960, which is this number with an E on it. That number with an E on it is scientific notation. It means it's a small number. It means I move the decimal point 4 places to the left. So 0.000495,198. I kind of have a hack for how to get that number. Since I know it's a number that's smaller than 1, if I add 1 to it, then that forces those decimals to move over. And then I just don't include the 1 there. So 0.000495,198. Okay, next one. Try it yourself. So this time we want the probability of being dealt 5 diamonds from a standard deck of playing cards that also includes 2 jokers. The joker is considered to be a wild card that could be used to represent any card in the deck. So probability that we are dealt 5 diamonds out of, now we have 54 cards and 2 are wild. So how does that change our problem? Now in our numerator, we need the number of ways to get 5 diamonds. But now, instead of 13 diamonds, I have these 2 wild cards. So I have 15 possible cards that would work for a diamond. And then I need the total number of ways to choose 5 cards. But now I don't have 52 cards, I have 54 cards. So take a moment, fill in these values, I am going to pause the video, which means that it's going to like start right back up with my stuff written in. So if you pause it now and then write your stuff down and then turn it back on, then you'll be able to check your answers. So the number of ways to get the 5 diamonds out of 15, since order does not matter, would be 15, a combination of 15 objects taken 5 at a time, which comes out to be 3003. And then number of ways to get 5 cards out of 54 would be a combination of 54 items taken 5 at a time, which is 3,162,510. Dividing that out gives me a probability of getting 5 diamonds when I have 2 wild cards would be 0.000949562. So almost twice as high a probability as getting the 5 diamonds out of 52 cards. Okay, example 8. Example 8. This is the challenge. We have a food manufacturer who is analyzing a sample of 400 corn kernels for the presence of a toxin. In this sample, 3 kernels have dangerously high levels of the toxin. 4 kernels are randomly selected from the sample. What is the probability that exactly 1 kernel contains a dangerously high level of the toxin? So here's what we're doing. We are figuring out the probability that when I choose 4 kernels, I'm going to get 1 that's dangerous and 3 that are safe. So it's the probability of 1 dangerous and 3 safe out of my 400 kernels in my sample. So remember back to our keywords. The word "and" means that we are going to be multiplying. So I am going to need to know the total number of ways to get 1 dangerous kernel. So I need the number of ways to get 1 dangerous out of how many dangerous kernels do I have? There are 3. So 1 dangerous kernel out of 3 times, because it's "and", so the number of ways to get 1 dangerous out of 3 and the number of ways, so times the number of ways to get 3 safe out of, well, how many safe kernels are there? I have 400 in my sample. 3 have dangerously high levels of toxins, so 3 safe out of 397 that are safe. And then I'm going to divide that by the number of ways for me to choose those 4 kernels out of the 400 in the sample. Now, does order matter? Well, am I going to be able to tell if my first one is dangerous and my next 3 are safe, or my first one is safe and my next one is dangerous and my next 2 are safe? Does it matter what order I choose them in? No, order does not matter. So I'm going to be using combinations, because permutations are the one where order matters. So my combination for the 1 dangerous out of 3, I have 3 objects and I am choosing 1. So it's 3C1 times, then to get 3 safe out of 397 would be another combination. I have 397 objects and I am choosing 3 of them. And then that's going to be divided by the number of ways that I can choose 4 kernels out of 400. So combination, I've got 400 kernels and I am picking 4. Okay, here comes the math. So we're going to do combinations, 3 kernels, choosing 1. That is 3. Times 397 kernels, choosing 3. That's that number. And then in the denominator, I have a combination of 400 objects that I am choosing 4 at a time. Oh, man. That's that number. So I am going to take 3 times that number, and I am going to divide that result by that number. And that is going to give me a probability of approximately 0.02955, which is about 3%. So if I choose 4 kernels out of 400, there's about a 3% chance that one of them is going to contain toxic levels, high levels of that toxin. Okay, here's another example that's going to be similar to that. So a jury consists of 5 men and 7 women. 3 jury members are selected at random for an interview. Find the probability that all 3 are men. So we want to find the probability that we are going to choose when we choose 3 members, that we choose 3 who are men, not mean, men, and we choose 0 women. So we're choosing 3 men and 0 women. So that is going to be, since it's an and, we're going to be multiplying. So that's going to be the number of ways to choose 3 men out of, there are 5 in the pool, times the number of ways to choose 0 women out of 7. And then we're dividing that by the number of ways to choose 3 jury members out of, we have 12 in our pool. Let's see, does order matter in this problem? When you're going on a jury, it really makes no difference if you're chosen first or last. So order is not important, which means we're using combinations. So to choose 3 men out of 5, that will be a combination of 5 objects taken 3 at a time. And then we're going to multiply that by the number of ways to choose 0 women out of 7. So we have 7 women. We're choosing 0 of them. Unfortunate. And then we're going to choose 12. Out of 12 people, we're going to choose 3 total for our jury. So if we do 5, a combination of 5 objects taken 3 at a time, that gives us 10. And then a combination of 7 objects that we're choosing 0 of, well, there's only one way to do that. And then combination of 12 objects chosen 3 at a time is 220. So the probability that when I select 3 jury members at random for an interview, and all 3 of them are men, even though 7 women were on the jury, it's going to be a low probability. 10 divided by 220, which is approximately 0.04545. That's repeating. So about 4.5%.